All right, I'm recording. Great. So from what I'm following is, yes, there is a way you can move those electrons over there to make that positive charge. And then you would have something like this. However, it's very important to note that you have positive charge here. When you made that resonance structure, do you have that positive charge? That's super important.
No, I didn't. So for the
Make sure you
first
have that
one,
positive.
I moved like both of them at the same time.
Yeah. See, in class and in the recording, the biggest tip he has is moving one step at a time. And my biggest tip for you guys, just straight up when you're approaching these, is whatever charge you have at the beginning, any resonance structure you have has to have that net charge. So for this compound in general, your net charge is just a -1. So for this net charge, it also has to be -1. And you see, wherever you create a negative charge, there has to be a positive charge that cancels it out because you have that negative charge there. Just like how we have hold on, in this problem, we have a net charge of +1. So whatever my new move you have has to ensure that the things are balanced. And it's a good idea, like I see it at, okay, if I have a system of sp2, 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 let me just move them around in one fell swoop like this. Like that. That is valid, but from your case, there's not really anywhere else you can go with that. And that's like the tricky thing he was trying to pull on you guys for this certain question. But again, the thing here, what's the net charge on this one? It's -1. Kaylin, does that answer your question regarding this?
Yeah, it does. Thank you.
It's something you have to look out for. Now that we have some people here, maybe I can start going over the moves and just basically the tips and tricks regarding our problem set. Because going back to here, the main issue I have, or main problem I have with people, is they're putting like double bonds down here. And the biggest thing I have to emphasize is there are cutoff points that you cannot encroach on. Because right here you have sp3 carbons. Okay. And these have hydrogens on them. That's something you can't really see with Kuklay structures, and that's something you really have to look out for, because if you have a double bond here, well, that's now sp3d, which we can't really have for carbon, and we can't just get rid of the hydrogens or else that would have a reaction. We can't do that on its own. This is not really resonance structure. So let's go over the moves. The easiest one is like a door hinge kind of thing. This double bond flips over here, and then whatever carbocation or carb anion charge, formal charge, just flips over. So your new resonance structure is something like this. And that works for a negative charge as well. So if you had like a super complex structure like this can switch over there. So charge is now here. And then same for this over here. Here, here, and here. And now your positive charge is over there. The door hinge move is super, super nice. Something you should get very used to. Looking at this, which one is the most stable out of the three? There's two of them. Maybe you go ahead. Thanks. Okay. I'm pulling up chat right now. If you guys want to put it in chat, you're also welcome to do that.
Be the first two, right?
Yeah, the first two is right now. Since all of these are all the same atom, you're looking at this substitution pattern: secondary, secondary, and primary. You want the charges to be on secondary because secondary atoms, because they can hybrid conjugate. Any hydrogens floating around here, they'll somewhat like conjugate and stabilize that to the best of their ability. Secondary is not ideal, but it's better than primary. The next thing is looking at very electronegative atoms. If they have lone pairs, they can donate them into a system. The thing here, you cannot add electrons just willy-nilly, because right here you have atoms that are sp3, so there are hydrogens there. You can't just conjugate and make pi bonds out of them. However, if this is sp2, that's an sp2 carbon because it's missing a pi orbital, you can donate that. So we have something like this. And look right here, we have a positive charge and then a negative charge. Net charge of -1. Nope, not -1, 0. And then net charge right here, again, we have 0. It's like, hopefully that's making a little bit of sense. And now we can probably take a crack at something like this. Okay, so right here we have a hexadiene kind of deal. And we just have a bunch of pi electrons. Now, the thing to note about this, all right, well, look at this. We have a conjugated system, sp2, 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 and sp2. However, this one is sp3. It's also sp2. This sp3 carbon doesn't play a role in conjugation at all. So if you had, for example, something like this, right? You have an sp3 carbon here. So this carbocation cannot skip over more than one carbon, because if this were to door hinge down here, it would form here. It would be nowhere, or this pi bond would be nowhere near that carbocation. So it can't just jump like that. Alternatively, what we can do is if we had a carbocation right there, this pi bond is right next to it because we have an sp2 here, and we can do a door hinge maneuver. Let me erase this. Door hinge maneuver over there and move that pi electron right there. So that's just what I'm trying to show with keeping everything sp2. And hopefully you guys are seeing a pattern. Now that we know all these sp2 carbons, we can start making some resonance structures. And for this specific type of problem set, they don't have to be good resonance structures. They can be something super unstable like this. It's a valid resonance structure. It's just not going to contribute to the hybrid model in nature. Like, it can exist, but it's probably going to be like a nanosecond of that structure is like, I don't know, time in existence. It's not going to be very common. Yeah. So going back to this, all right, well, we don't have any charges we can move around. However, we can move some pi bonds around because we have an oxygen here. We can't door hinge any of these pi bonds yet. However, we can lump it onto that oxygen. And again, one step at a time. We don't move like a lone pair and a pi bond in the same move. It's a good idea to just do one step at a time. So if we move that one pi bond up there, don't forget your formal charge, we would have a compound like this. And again, look at the pattern. Net charge of 0. Let me erase this so you guys can take a better look. All right, we have a net charge of 0. And again, right here, we have a net charge of 0. There's that negative, and you have that positive. Again, whenever you make a negative charge or lump some kind of positive negative charge onto a certain atom, you have to have a counter charge to maintain that. Because wherever an atom loses electrons, one has to gain it. So if you had like an alkene like this, you're more than welcome to lump all of these atoms onto that one carbon to the point where you have something that looks like this. Nope, not that. This. Like that. Again, the net charge is 0, but that's entirely possible. Not really common, but something good to know for resonance structures. All right, let me remove the pink around here. And now we have that negative charge there and that positive charge here again. Now we have some more stuff to work with because these charges can move around with our, again, door hinge maneuvers. So we can move this pi bond over there. if we were to have that, we would have positive charge here. And like that. Now, again, look at the charges, -1, +1. Our net charge is still 0, so it gets my thumbs up. Now, there's one more resonance structure, but where can we go? Like this pi bond can't really go all the way over there. Well, the thing is, we can make another resonance structure from that one. What if we were to instead go from this? So we went from that pi bond instead, we would have a compound that looks like this. And again, your final check should be the net charge. It's 0, just like all the others. Is that making a little bit of sense? Or is everyone following?
Yep.
Right. And now let's introduce some heteroatoms. So that was just something like I was drawing. But heteroatoms introduce a lot more complicated stuff. But once you get it, you kind of get it. By the time you get to second semester, you're pretty much going to be a master at residence. It's going to be one of the easy questions on the test. So right here we have, all right, sp3, but it can donate electrons. But right here we have sp2, sp2, sp2. And we have a system because they're all next to each other. There's no sp or sp3 carbons that interrupt anything. Something I saw that I would refrain against is if you have like a lone pair and then an alkene next to it, you can't donate those electrons just yet because, well, then you would have something like this where you have carbon and then double bond there. And then that hydrogen now is still there. That's 5 bonds. You can't overload a carbon, or nor can you add lone pairs to an alkene to make an alkyne, because you're changing the hybridization. If you change an alkene to an alkyne, well, you're making sp carbons rather than sp2. So the key hybridization for resonance is sp2. So for this structure, let's just take a little gander. So we know that the net formal charge is, again, 0. Now we can take a look at some valid resonance structures. Let's make some moves. So looking at this straight up, we have 2 formal charges and we have some electrons that we can move around. Well, first off, we cannot move those electrons down there because this is already sp2. If we moved it down there and made a double bond, that carbon would have 2 double bonds and 1 sigma bond. Those are 5 bonds in total, and carbon cannot have that many electrons in its octet. So what if we were to look at this positive charge? Well, we can do something with that. We can door hinge that pi bond over there. Oxygen, nitrogen. Which carbon would that positive charge be? 1, 2, or 3?
Three.
Yeah, it would be a 3.
Everything's finally clicked.
Yeah, I just saw your message. Positive charge would be right there. Now that the positive charge is here, we can make a lot more resonance structures. Now, no, I'll get to that later. We have 2 spots where resonance structures can form. We have a double bond that could form between that carbon, the oxygen, or the nitrogen, because both of them have lone pairs that can donate. Now, real quick, the net charge is, look at it, 0. If we were to move it up to the oxygen, let's go ahead and try that out. NH2, that oxygen right there. Now that we did that, look at that. That is a very valid resonance structure. We still have our sp2 carbons. Our net charge is 0. There's no formal charges at all. Now, what if we were to take a look at that carbon-nitrogen bond? We would have something like this. Don't forget the formal charge there. There we go. Something like that. And look at the formal charges. That adds up to 0. So you have a total of 4 resonance structures there. Now the real kicker is asking you which one is the most stable. Now, looking at this at a glance, which one looks the most stable? 1, 2, or 3?
2.
Yes, actually. Some people might think 1 because, well, look at that. We have a tertiary carbocation. Well, the trick to look at the most stable, there's one main rule you have to look at. So if you're taking notes, write this one down. So the most stable, first of all, or the most number of bonds. Because molecules, whichever resonance structure has the most amount of bonds is the most stable. Because rather than having formal charges or dumping a bunch of electrons on an electronegative atom, electrons are in a pretty stable form in a bond. So the more bonds it has, the more stable it is. So look at this. We have one bond, or pi bonds, the most pi bonds. One bond, one pi bond, 2 pi bonds, and 2 pi bonds. So it's either going to be one of these compounds. Now let's look at the formal charges. Number 2 does not have any formal charges, while number 3 has formal charges that are relatively close to each other. So it's kind of easy. This one is the most stable. Now there's one last thing we have to cover in regards to the most stable. What if you had something where, all right, hypothetically, let's create a situation where we have a carbocation something like this. Let's have an ether. And then let's have an group. And let's just make an imaginary long compound. All right. Now the 2 possible resonance structures here. Let's make one blue and let's make one green. So if the green route, let's make that the amine route. So this has a lone pair of electrons that could donate. So there would be double bond there. And then the positive charge would be here, CH3, CH3. And then we would have an ether right here. Again, look at that net charge. Net charge is +1. This net charge is +1. So that checks out. In contrast, we have a blue group, see, ether, H3. However, these electrons go there. So I have a double bond there, and then you have an amine group. I'm just going to write it like that to save some room. Now your positive charge is on that oxygen. Now, wait, first off, +1 charge, still good. Now, which one is the most stable? This one's also really tricky that you might see on the test. So these have an equal number of bonds. So that's the first thing you look at. But what if they have, or the most amount of double bonds? If they're equal, now what do you look at? Well, you have to look at where that positive charge lies. And for here, you want to look at electronegativity. Negative charges, you want on atoms like a halogen, like chlorine, or iodine, or oxygen. Positive charges, you want on like carbon or nitrogen, because these are a lot more electropositive. That's a term you should know, electropositive. So when you're looking at the positive charges on in oxygen compared to the positive charges of nitrogen, the nitrogen positive charge is a lot more stable because nitrogen can carry that positive charge a lot better than oxygen. Because if you're looking at electronegativity, oxygen is a lot more electronegative. So if you take the what is it? The converse of that? Nitrogen would be the most electropositive. Does that make sense for you guys?
Yes.
Great. So let's take a look. Yeah, these were just little annotations. Okay, so let's take a look at the problem set. Let's just start from square one. So right here, we have a structure right here. So we have